Next, we're going to talk about acid-base reactions or proton transfer reactions. Let me show you an outline of the topics we're going to be talking about. First, we'll discuss the different definitions we have for acid-base reactions, and then we're going to talk about several things that can have an impact on the acidity of a given molecule. Look at trends in the periodic table, inductive effects, resonance effects, and we'll wrap up by looking at some common acids and bases. Now, most students coming through general chemistry, having a year of general chemistry, will know that there's two main definitions for acid-base reactions, having Lewis acids and bases and Bronsted-Lowry acids and bases. Okay, a Lewis acid is something that's described as an electron pair acceptor. So this has to do with electrons. We describe this as an aprotic acid. We'll find that the other type of acid, the Bronsted-Lowry, is one we call a protic acid. We'll see that next. And how can something accept a pair of electrons? Well, it's something that will have a vacancy that has no octet. So some common Lewis acids are things like BF3 or AlCl3. These molecules, when you take a look at their detailed Lewis structure, you find that there's a vacancy on this boron. It's missing an octet. Same thing with the aluminum. It has only 3 bonds, and we know that atoms want to have a filled octet, and they would readily accept a 4th bond, and so that's what makes them electron pair acceptors and excellent Lewis acids. A Lewis base, then, is something that can donate a pair of electrons, so something with either a lone pair of electrons or maybe a pi bond. These would make very good Lewis bases. So let's see an example. If we reacted ammonia with AlCl3, we said AlCl3 would be a good example of an acid, a Lewis acid. I'm going to put this in quotes because it's a Lewis acid. And ammonia would be a good example of a base because it has a lone pair of electrons. And the reaction we would expect to have happen between these two is that the nitrogen would share its lone pair of electrons with the aluminum and form a bond. So we're going to form a new bond between nitrogen and aluminum. And this would be our product of this Lewis acid-base reaction. And because of this new bond, we're going to have some formal charges now on the nitrogen and the aluminum. This nitrogen has 1, 2, 3, 4 electrons around it. We know nitrogen wants 5, so this nitrogen now has a positive charge. And this aluminum also has 1, 2, 3, 4 electrons around it. But aluminum only wants 3, so it has an extra electron, and we would have a negative charge on the aluminum. So this is the product of our Lewis acid-base reaction. And let's just take a look at one more example. A carbocation is another good example of a Lewis acid because it is missing an octet and can accept a pair of electrons. Water could be used as a Lewis base. And so, same idea, we could use that lone pair to form a bond between the oxygen and the carbon. What does our product look like? We now have a new bond between carbon and oxygen. And what does this oxygen still have on it? It still has 2 hydrogens. And any lone pairs? Well, one lone pair is now being used as this sigma bond. The other lone pair is still there. So this would be the product of this second reaction. And again, let's check our Lewis structure and check for formal charges. This carbon now has 4 bonds, so it's neutral. But this oxygen has 1, 2, 3, 4, 5 electrons. We know oxygen wants 6, has only 5, so it's missing an electron. So we would have this positive charge here. So these are a few examples of some Lewis acid-base reactions. But in organic chemistry, we typically don't refer to such reactions as acid-base reactions. We're going to have a new name for Lewis acids. We're going to call these electrophiles, things that love electrons. And we're going to call Lewis bases nucleophiles. So we will see reactions like this down the line, further down in our lessons. But when we do so, we're not going to be calling them Lewis acids and bases necessarily. We're going to be describing them as electrophiles reacting with nucleophiles. So for organic chemistry, when we're discussing acid-base reactions, we're talking about the other definition, the Bronsted-Lowry type. And in a Bronsted-Lowry definition, a Bronsted-Lowry acid is an H plus, which we call a proton. It is an H plus donor to be a bronzolari acid. That's why we call this kind of acid a protic acid, because it is one that donates protons, that is a source of protons. And a bronzolari base is a proton acceptor, something that can take a lone pair of electrons. So the reaction, an acid-base reaction then can be described as a proton transfer, a transfer from an acid to a base. Now the mechanism for that transfer is not the hydrogen atom flying over to the base, okay? Because our mechanism, when we use curved arrows, is showing electrons moving. So instead, it is the lone pair of the base, or whatever electron source the base has, the lone pair attacking the proton and then breaking the HA bond and having those two electrons go to the remainder of the acid structure. So our product then will now have the base with a new proton on it and the A group with a new pair of electrons on it. Now if both the base and the acid are neutral, as shown, the base, after you add a proton to it, after you add an H plus, will now be positively charged. And the A, after losing an H plus, will be negatively charged. So you'll have these charges if we started out neutral in both cases. After a base has accepted a proton, we call that new structure the conjugate acid of that base. So a base is related to its conjugate acid by protonation. And the structure that remains after an acid has lost its proton is known as the conjugate base of that acid. So an acid is related to its conjugate base by losing a proton or donating a proton. So this is called a proton transfer reaction. And what we have here, as shown, is an equilibrium. We have two acids and two bases in competition on who's going to donate the proton and who's going to accept the proton. Because if you look at this reverse reaction, the reverse reaction would also be described as a proton transfer reaction, right? This now is a proton donor, and this is a proton acceptor, and these products would be the result of a proton transfer. So we have a competition for this equilibrium, and the rule is that the equilibrium lies in the direction of the weaker acid-base pair. The weaker acid-base pair. This is an important rule to keep in mind. We'll see lots of examples of this as we move along. So if this equilibrium lies in the direction of the weaker acid-base pair, we're going to have to be able to determine which pair that is. So how do you decide who the stronger acid is? Well, if you're lucky enough to have a pKa table, you can use that. Or perhaps you can predict that yourself, and that's what we're going to be focusing on in this lesson, is looking for features that affect the acidity and make something a stronger acid or a weaker acid. Okay, but here's an example. Let's say we have water acting as an acid and ammonia acting as a base. Let's see what that proton transfer reaction would look like. Okay, the acid donates one of its protons to the base, so our mechanism is the base grabs the hydrogen, leaves the electrons behind on the oxygen. So what does water look like after it has been deprotonated or has donated a proton? We only have HO with 3 lone pairs. And that means we have an O minus. 1, 2, 3, 4, 5, 6, 7. Oxygen only wants 6. So we have an extra electron there. So that's the conjugate base. And what does the conjugate acid of ammonia look like? It is, instead of NH3, it's going to be NH4. So you could just draw it as NH4, or I can draw it out to show the new hydrogen for emphasis. And that's also going to be charged. This nitrogen has 1, 2, 3, 4 bonds, 4 electrons. It wants 5. So this is going to be N+. We're going to get this ammonium, NH4+. So if we took a look at this equilibrium and asked in which direction does the equilibrium lie, does it lie in the forward direction or the reverse direction, what we can do is we can look up the pKa's of the two competing acids. In the forward reaction, water That has a pK of about 16. In the reverse reaction, the ammonium is the acid, and that has a pK of about 9. Now, what is the relationship between pKa and acidity? They have an inverse relationship. The lower the pKa, the higher the acidity. Let's remember that. The lower the pKa, the higher the acidity, the stronger the acid. So a pK of 9 is a stronger acid, and a pK of 16 is a weaker acid. So where does the equilibrium lie? It lies in the direction of the weaker acid-base pair. So it's going to be going from the stronger acid to the weaker acid. The equilibrium lies to the left. Is one way to describe that. You could also say that the reverse reaction is favored. Okay, and we can make that conclusion simply by comparing the two acids. Now, we said that it's going to be the weaker acid-base pair, and it turns out that once you've identified who the stronger acid is, that's also going to tell you something about the conjugate bases. Okay, if ammonium has a pK of 9, this is the stronger acid, its conjugate base is going to be the weaker conjugate base. Because an acid and its conjugate base also have an inverse relationship. A stronger acid has a weaker conjugate base. The weaker acid water has the stronger conjugate base. So once we identify the weaker on one side of the acid, it will always correspond with the weaker base being on that same side. So we don't have to compare both the acids and the bases. We just need to find a difference in one or the other, and that should be enough to answer our question. Well, we can just kind of mention here the stronger acid has the weaker conjugate base. And the weaker acid has the stronger conjugate base. So you can see how we ended up labeling those two bases. Okay, so this is how we can decide the direction of an acid-base equilibrium. Let's take a look at some factors that might affect the acidity, the strength of an acid. And one thing we can do is we can look at periodic trends. Let's take a look across a row of the periodic table. Carbon, nitrogen, hydrogen acids. All of these have hydrogens on them, so they can possibly donate a proton. They could be potential acids. And given are the pKa's, methane, CH4 has a pK of about 50, ammonia has 38, and water has about 16. So who's our strongest acid here? The lowest pK is the strongest acid. And the pK of 50 is the weakest acid. Now let's take a quick note about, pKa's. Let's take a look at the difference here, 50 to 16. That's a difference of 34 pK units. Does that mean that water is 34 times more acidic than methane? That would be pretty significant. But no, remember that the pKa table is a logarithmic scale, so we're looking at orders of magnitude, factors of 10. So there is a one with 34 zeros after it times more acidic. So that's like a gajillion. We don't even know what number that is. So this is hugely, hugely more acidic. And we need to be able to understand that. We need to be able to rationalize that and have an understanding for these pKa's. So the way we're going to answer the question of why is there such a huge difference in their pKa's when you go across the row in a periodic table, what we're going to do is we're going to look at the conjugate bases of each of these. Look at the conjugate bases. So if water acts as an acid, what is the conjugate base going to be? We're going to lose an H+. That's going to give hydroxide, HO-, as a conjugate base. How about ammonia? Ammonia has one lone pair of electrons. So after we lose an H+, we'll have NH2. Now with two lone pairs, also a minus because we're losing an H+. And methane, CH4, can see a trend here. We'll now have CH3 with an extra lone pair and a negative charge. So these are our three possible conjugate bases, and what we want to do is try and look for a difference in their stability. Well, what's the most significant difference as you move across the row in a periodic table? You're going to be increasing in electronegativity. So oxygen is the most electronegative atom compared to carbon and nitrogen. And what effect is that having for us? Well, let's start by writing the fact here. Oxygen is more electronegative than the others. And so is that a good thing for that negative charge to be on a more electronegative atom? Absolutely. So what we can say is that the oxygen better handles the negative charge. That means that hydroxide is the most stable conjugate base. Hydroxide is the most stable of these three species, the C- versus the N- versus the O-. This is the most stable. Now, what is the relationship then between stability and reactivity? Well, the more stable something is, the lower in energy it is, the less reactive it is. So because it is more stable, hydroxide is the weakest conjugate base. It is the least reactive. Now, what do we know about something that has a stable, unreactive conjugate base? What does it tell you about the parent acid? It must be a strong parent acid. So hydroxide has the strongest parent acid. And does that agree with our pKa data? It sure does. That had the lowest pKa, and yes, water was the strongest acid. Okay, so it's going to be the stability of the conjugate base that is going to answer so many questions about the strengths of various acids. Now let's go through the argument, the opposite argument for over here, on why this is maybe not such a great conjugate base. Okay, what we can say here is that carbon is the least electronegative of all of these carbon, nitrogen, oxygen atoms. Okay, and so this is the least stable conjugate base. And if this is the least stable, unstable conjugate base, that means it is the most reactive conjugate base. It's the strongest conjugate base. So this is the most reactive, strongest conjugate base. Okay, the reactivity, the relationship between stability and reactivity for molecules is very similar to that of people. Okay, the more stable you are, the more calm and cool and collected you are, you're pretty unreactive. Okay, and the same is true for molecules. But if you're high energy, unstable, that makes you very reactive, very volatile, and we're going to find that same relationship is true when we're looking, comparing people and when we're comparing molecules. So if this one is the strongest conjugate base, what does that tell you about the parent acid? We know that this has the weakest parent acid. And that's what our pKa data tells us. pK of 50. This is a horrible acid because carbon hates having a negative charge. It's so electropositive. So our goal, and what this is demonstrating here, and what we'll find again and again and again, is that the stronger acid has the more stable and therefore weaker conjugate base. Okay, and one thing that can help stabilize a conjugate base is the electronegativity of the atom on which a negative charge resides. Let's take a look at an energy diagram that might help illustrate this concept. If we're comparing methane and ammonia and water as acids, we know that water is the strongest acid. And that's because when we compare the difference in energies of our conjugate bases, we see that the more stable conjugate base is the one with the negative charge and the most electronegative atom. Okay, so right here, this is the most stable conjugate base, meaning it's the lowest in energy. Okay, how about the energies of our starting materials? Well, these are all neutral stable molecule, so these have all about the same energy. There's not any significant difference in the energy of the starting materials. The significant difference in energies is the atoms bearing the negative charge. So when we compare these processes, which of these would prefer to be an acid and donate a proton? Well, this process looks the most favorable. This is the least endothermic. This is the most favorable reaction. And that's why water is the strongest acid. So once again, we're going to look for differences in the stability of the conjugate bases. The more stable the conjugate base, the stronger the parent acid. What makes an acid a good acid? It doesn't mind donating a proton if it doesn't mind where it's going to. If it's going to a conjugate base isn't in a stable, happy place, that makes the parent acid more likely to donate its proton. Let's see another example. Another periodic trend is when we're going down a family or down a column on the periodic table. So let's compare HF, HCl, HBr, HI. Here we have our pKa's. So of these pKa's, who's our strongest acid? Well, the lower the pK, the stronger the acid. In fact, the more negative the pK, the stronger the acid. So HI is the strongest acid. That is stronger than HBr, than HCl, and then HF. HF is the weakest of all the haloacids. And let's see if we can explain this again. Now, the way we're going to explain it is, if we ask why do we have this difference in pKa's, once again, we're going to look at the conjugate bases. So what does the conjugate base of HF look like? That means HF is going to act as an acid, is going to donate a proton, and that leaves behind F-. HCl gives Cl-, HBr gives Br-, and HI gives I-. Now, where do we go from here? We try and find something that will explain a difference in stability between these different conjugate bases. Now, what's the most significant difference as you move down a column in a periodic table? Yes, the electronegativity does change as you move down a column, but a more important difference is going to be the size of the atom as you move down and you add a shell of electrons on each new row. Okay, so it turns out that iodide is the biggest ion and fluoride is the smallest ion. So that's the fact, that's the difference between these, all four of these. How do we relate that to stability? Well, let's think of this ion as having a negative charge. A negative charge tells us we have an excess of electron density. And if you can spread that negative charge out over a larger surface area of the large iodide, then that's going to be more delocalized, and that's going to be a more stable charge. Okay, so what we say about the I- is that the negative charge is dispersed or delocalized. That's a very good word. That means it's not in one small location. It's delocalized. It's spread out over several locations. And that means this is the most stable conjugate base. Now, where do we go from here once we decide which is the most stable conjugate base? Most stable always means less reactive. So this is the least reactive and therefore weakest conjugate base. Now we have something about the strength of the conjugate base. The weakest conjugate base has the strongest parent acid. And does that agree with our pKa? It does. This had the lowest pKa, so yes, HI is the strongest acid. Okay, what would we say about fluoride? Why is fluoride so much less acidic, so much less likely to donate a proton? Well, here we have a very, very small surface area with that negative charge, so we could describe this as kind of an intense negative charge, compact, intense. That makes it unstable. It's an unstable anion to be on such a small surface area. If you are unstable, that means you are more reactive. This is the most reactive and therefore strongest conjugate base. And the strongest conjugate base has the weakest parent acid. Okay, so in this case we can see the size of the atom having an impact on the stability of the negative charge in the conjugate base. Let's take a look at some inductive effects that we might have to explain differences in acidity. If we ask which is the stronger acid here, we have CH3OH versus CF3OH. Now, in this first structure, if we expected this to be an acid, there's two different types of protons that can be donated. One of the hydrogens on the carbon or one of the hydrogens on the oxygen. Now, which of those hydrogens do you think is going to be the most acidic? We just saw the periodic trends, and we know that because oxygen is so electronegative, that would much prefer to have the negative charge. So what we're doing is comparing this OH with this OH when we're comparing the acidity. And how are we going to distinguish between these two? Well, once again, let's look at the conjugate bases and see if we can find a difference. CH3OH, the conjugate base would be CH3O minus. CF3OH, let's draw out these fluorines because that's obviously the difference between the two molecules. We either have CH3 or CF3, and we have an O minus versus an O minus. So this is a case where periodic trends are not going to help us because the negative charge is on the exact same electronegative oxygen in each case. So now we look elsewhere in the molecule to see if there's something that can maybe stabilize or maybe would destabilize the negative charge. Clearly we have these fluorines here, and so let's think about what effect that's going to have on the negative charge. We'll start by stating the fact that we know about fluorine, and that of course is that fluorine is more electronegative than hydrogen. That's what we're comparing it to in this case. Of course, fluorine is more electronegative than everything. But we know that fluorine is more electronegative. And what does it mean to be electronegative? It means that fluorine pulls electron density toward itself. So let's also state that fact. We have an inductive withdrawal of electron density by fluorine. We have an inductive withdrawal of electron density. We can show that with an arrow like this. We could say that the fluorines, each of these fluorines is pulling electron density toward itself. These arrows show the movement of electrons through these sigma bonds. That's what we call an inductive withdrawal, inductive effect. Okay, now here's the tricky part. Is that a good thing for the negative charge, or is that a bad thing for a negative charge? And typically when I survey my students on this question, I get about a 50-50 split. Well, let's think about what it means to have a negative charge. A negative charge tells me that there is an excess of electron density on that oxygen. That's not a good thing. It would rather be neutral. Okay, and what are these fluorines doing? They're helping to pull some of that electron density away from the oxygen, bringing it closer to being neutral. In fact, you can imagine that each of these fluorines is sort of taking on some of that negative charge. It looks like we are delocalizing that charge a bit. Is that a good thing? That sounds like a good thing. And that is in fact. Okay, this stabilizes. This stabilizes the negative charge. We could again kind of think of it as delocalizing. It delocalizes it. Okay, and so this is, if this is the more stable conjugate base, what does that tell you? This is the more stable and therefore less reactive, meaning weaker. This is the weaker conjugate base. And the weaker conjugate base, this has the stronger parent acid. So that was our original question. Our original question, which is the stronger acid? And the acid with the fluorines on it is going to be the stronger acid. This is more likely to donate its proton because the resulting anion in the conjugate base will be stabilized by the fluorines, the inductive effect of the fluorines. So we could describe fluorine as an electron withdrawing group. We can abbreviate that EWG. We're going to be seeing that abbreviation a lot down the road. And let's take a quick look at some other common EWGs, electron withdrawing groups. For example, if we have a nitro group, an NO2 group, I've drawn it out here. Okay, this is also something that would pull electron density toward itself, just like a fluorine did, right? We said a fluorine pulls electron density. A nitro would do the same thing because of that N+. Now a cyano group, a CN triple bond, has the same effect, and even though it's not charged like the nitro, because nitrogen is more electronegative than carbon, and because we have some resonance here, there's a partial minus on this nitrogen and a partial plus on this carbon, and therefore this also pulls electron density toward itself. It would be an electron withdrawing group. And a carbonyl also has resonance that puts a partial positive on this carbon and a partial minus on this oxygen, and so that partial positive carbon causes an inductive withdrawal. We can see it can also do stabilization by resonance. And any halide is going to be electronegative and can pull electron density toward itself. So not just fluorine, but also the others, chloride, bromide, iodide. And so what these have in common is these would all stabilize. An adjacent negative charge. These would all stabilize an adjacent negative charge. What if I had a positive charge next door? Now, we're not going to see that in a conjugate base, but what if I had a positive charge, an electron deficient site here? Would it be a good thing to have a fluorine on that? Or a nitro or a cyano pulling even more electron density away? That would be a bad thing. So we could make a little note here, and it would destabilize a plus charge. That might become important down the road if we ever saw that when we're exploring the effects of electron withdrawing groups. Now, one thing that we will note about inductive effects is that these are something that decrease with distance. The further away we put that electron withdrawing group, the less effect it's going to have, because simply there's more bonds to travel through. Inductive effects are looking at the electrons in sigma bonds being pulled toward a more electronegative atom or a more electronegative group, and so that's why we see a decrease with distance. So if we take a look at these acids, these are all carboxylic acids. We see this group here, a carbonyl with an OH, and that is the group that we're going to have. That's going to be our acidic group. It's the OH there. So they all have similar looking conjugate bases where we have an O- next to this carbonyl. So they'll all have very similar conjugate bases. The only difference is what's attached to the carbonyl. Here we have just a CH3 group. Here we've put a chlorine somewhere down the chain. Here we've put a chlorine again. Here we put a fluorine. And what do we see as an effect on the pKa's? We see that as soon as we put a halogen on here, we lower our pKa. And in fact, this is going to be the most acidic with the lowest pKa. And why is this the most acidic? Well, that's because the fluorine is more electronegative compared to the chlorine. Okay, so this has the most stable and therefore weakest conjugate base. That fluorine is going to help stabilize that conjugate base the best, right? It's going to pull electron density away from the conjugate base. That's going to be a good thing. So this is the strongest acid. Okay, compared that to having a chlorine, that chlorine is making it not quite as acidic. And how do we compare these two? They both have a chlorine, but this one is situated a little more closely to where the negative charge will be in the conjugate base. This one is a little further down. So we see if we have the electron withdrawing group is farther away and less effective. So while they all pull electron density away, the fact that he's not as close to the O- means that he's not going to have as big an impact on the pKa. Okay, and why does this have the highest pK of all of them? Why is this the weakest acid of all of them? Because this has no electron withdrawing group. There's nothing there to help stabilize the O- in addition to, they all have the same O-, so there's nothing additional here to stabilize the negative charge that the others have. Okay, so this has the least stable and therefore the strongest conjugate base. And of course this is the weakest parent acid. Okay, so if we have to compare electron withdrawing groups, the closer we can get that electron withdrawing group to the charge that we're trying to stabilize, the better. Now let's take a look at using resonance to help stabilize a conjugate base and what effect that might have on the acidity. If we take a look at these two OH-bearing compounds, these both have OH groups, so that they can be, those are reasonably acidic. But this one has a pK of 16 and this has a pK of 5. Now again, that's 11 zeros. That's a huge difference in pKa. And let's see if we can explain what that difference, where that difference comes from. If we look at the conjugate bases, we're comparing an O- to an O-. So once again, we can't think of any difference in periodic trends because each of those oxygens is equally electronegative. And we might say, well, this carbonyl can have some electron withdrawing effect on that oxygen to help stabilize it. But we just saw that inductive effects, maybe have an effect of 1 or 2 pKa units, certainly not making it, trillions times more acidic like this one is. So what's the difference here? Well, if we take a look at this O-, I recognize that this lone pair is allylic. It's next to a pi bond, which means we can have resonance with that lone pair and that pi bond. And what does that resonance do? It moves the negative charge to a new location. Okay, anytime you can delocalize the charge through resonance, that's going to be a really great effect. So what we could say here is that conjugate base 2 is resonance stabilized. Resonance stabilized. You could say it's stabilized by resonance. Resonance is always a good thing and will always have a big impact on stability. Okay, that tells us that conjugate base 2 is the more stable, weaker conjugate base. And that's why conjugate base 2 has the stronger parent acid by far. A pK of only 5. Okay, so resonance will have a tremendous impact on the acidity of a compound. Now, one thing I want to consider, though, is you might look at the starting compounds and recognize that even the starting acid has some resonance stabilization, right? Because this also had an allylic lone pair. And there's another resonance form we could draw for this. So you might ask, well, which of these resonance stabilizations is more significant? And the answer here is when you think about which resonance form contributes more to the overall picture, that will tell you how significant the resonance is. Here we have an O-, and here we have another O-. Which of these is the better contributor? Which will contribute more to the overall hybrid? Well, the answer is they're equally contributing. And so what we have in the case of this conjugate base is that we have a large amount of resonance stabilization. In fact, when you have two equivalent resonance forms, that's the best stabilization you can have. So this really delocalizes the negative charge. You can put that down here again. This is so important. Delocalize negative charge. Okay, and while this does have some resonance, because now we've created formal charges, this second Lewis structure is a very small contributor to the overall picture. And so even though it exists, what we have here is just a small amount of resonance stabilization. And it turns out that this will be not significant. The more significant resonance that clearly does have an impact on the pKa is the stabilization of the conjugate base. And maybe if we take a look at an energy diagram, we might see that pictorially might make a little more sense. So we said that the stabilization of this parent acid was small, and the stabilization of the conjugate base was large. And if we take a look at an energy diagram, when we compare the parent acids, 1 and 2, we might find that there is, in fact, a small difference in stabilization because 2 does have a small amount of resonance. Okay, but whatever small difference there is, that is not significant, not as significant as the large amount of resonance stabilization that we have comparing the O- in the conjugate base 1 and the resonance stabilized delocalized O- in conjugate base 2. So we have a large amount of resonance, so there's a large difference in energy. And so once again, this transformation from 2 to conjugate base 2 is the least endothermic and the most favorable. So what we're going to be looking for, okay, something to bear in mind is that the most significant resonance stabilization that we can look for, of all the resonance that we're looking for, is we want to find a way to delocalize the negative charge of the conjugate base. We want to be able to move that conjugate base around. So the most significant resonance stabilization is delocalization of the negative charge. So if there is a way that you can move that negative charge to a different location because of resonance, that's going to be something that will lead you to the correct answer and the correct conclusion. Let's see another example. How about if we compare these 3 compounds? Again, we're looking at 3 compounds bearing OH groups. But we're trying to see which of these OHs is going to be most likely to donate a proton and therefore be the strongest acid. And because we're comparing 3, let's also see if we can decide which would be the least acidic, which would be the least likely to donate a proton. As usual, the answer is going to reside, since these are all neutral stable molecules, the answer is going to reside in the structures of the conjugate bases. So conjugate base 1 has this O-, conjugate base 2 has this O-, conjugate base 3 has this O-. And what we're going to do is try and find a difference in their stability. Do any of these have resonance? That might be a good thing to look for. This one has some resonance because we have a carbonyl. This has some resonance. We can draw an O- C+. So we have that resonance. Does this one have resonance? Can we take this negative charge, take that lone pair, or move it in here? Would that be a way to delocalize that negative charge and move it around? No, we can't do this because this carbon already has 4 bonds. It has no place to move its electrons, so that would just be 5 bonds. So this has no resonance. Okay, this has some. We'll see what relevance that has here. And how about this last one? Does this have any resonance? If we take a look at these lone pairs, we see that they are allylic to a pi bond next to a pi bond. So yeah, this does have resonance. we can draw a new Lewis structure that uses one of those pi bonds. This carbon now will have the negative charge. And are there any other resonance forms? There are, actually, because this lone pair is still allylic. So we can move that in. Anytime we have a allylic resonance, we make the lone pair a pi bond, make the pi bond a lone pair. Any more resonance? Yeah, in fact, we can continue moving this around. We'll just say etc. here because we've kind of made our point that we can move that negative charge around. And so when we look at the two possible resonances for compound conjugate base 2 and conjugate base 3, what I see in conjugate base 3 is these resonance forms actually relocate the negative charge, delocalize the negative charge. So that's going to be excellent resonance. So let's say that about conjugate base 3, we have very good resonance stabilization. And that's because we have delocalized the negative charge. So this is most definitely going to be the most stable conjugate base. The most stable conjugate base is the weakest conjugate base. And the weakest conjugate base has the strongest parent acid. So this has the strongest parent acid. And so we would expect 3 to be the most acidic. Okay, how about if we compare 1 and 2 now? If we're looking for who would be the least acidic, is there any difference between 1 and 2? Now, 2 has some resonance, but notice it doesn't help move that negative charge. But does it do anything to, is it something that stabilizes the negative charge, or is it something that makes it worse? Well, having a positive charge there would help take some of the electron density away from that oxygen, wouldn't it? In fact, we saw the carbonyl acting as an electron withdrawing group, and so this, in fact, would be a good thing for the negative charge. So let's make the point first that the resonance, because it does have a resonance form, but the resonance does not delocalize the negative charge. So it's not as good as conjugate base 3, but the inductive effects of the carbonyl, if it's acting as an electron withdrawing group, the inductive effects makes it more stable than conjugate base 1. So even though this resonance doesn't help move the negative charge from the oxygen, it helps pull some of that electron density away inductively. So the fact that we have an electron withdrawing group, much like we saw the fluorine doing that behavior, means that this is going to be the second most acidic compound, and then compound 1 is the weakest. So because this has no resonance, this is the least stable, and therefore strongest conjugate base. So this has the weakest parent acid. So compound 1 is the least acidic. So we have a combination. In this example, we have a combination of both inductive effects and resonance effects. When we have both of those acting, like we do in this case, it's the resonance effects that are generally going to win out, because the resonance effects are going to be ones that really delocalize charge and add stability. How about if we turn it around and looking at an acid-base reaction and try and answer the question, which is the stronger base? Same question as asking which is more basic. Okay, we're comparing CH3OH versus CF3OH. Okay, and how are we going to answer this question? Well, let's take the same approach we did for the acids. In the acids, we looked at the conjugate bases. So when we're comparing bases, we're going to look at the conjugate acids. In other words, let each of these be a base and see where it takes us. So let's protonate in order to look at the conjugate acids. So just like an acid donates a proton, being a base means that you accept a proton. If we imagine this reacting with some acid, it can take a proton from that acid. So what does the conjugate acid of this base look like? It will now have 2 hydrogens on that oxygen and just 1 lone pair. That gives us an oxygen with 1, 2, 3, 4, 5 electrons. It wants 6, so it'll give us an O+. If you add an H+ to a neutral molecule, you end up with a positively charged molecule. Okay, so that's conjugate acid 1. Conjugate acid 2, same thing, except this is an oxygen, except instead of a CH3, we have a CF3. Okay, so let's draw our conjugate acids and let's look for a difference in their stability. So just like we did for the cases of deciding who's a stronger acid. So what's the difference between these two? Well, once again, we see that we have fluorine versus hydrogen. So let's make the note. Let's start by stating the facts. Fluorine is more electronegative than hydrogen. Okay? That means that it withdraws electron density and it withdraws electron density inductively, right? So the effect we have going on is something like this. Each of those carbon-fluorine bonds are polar in the direction of the fluorine. It pulls electron density, so that makes this bond polar as well, and it pulls electron density. I mean, it's an EWG. So here's the question. Is that a good thing or a bad thing? In this case, we're looking at a positive charge. That tells us that this oxygen is electron deficient. It's missing electrons. And what are those fluorines doing? They're pulling even more electron density away, making it even more making it even more positively charged. That doesn't sound like a good thing. That sounds like a bad thing. So what we can note is that this destabilizes. This destabilizes the plus charge and makes conjugate acid 2. Remember, we're looking at conjugate acids 2. The less stable. Less stable means more reactive. Let's put that in there. More reactive and therefore stronger conjugate acid. Because this is unstable, it's now going to be the stronger acid. The stronger conjugate acid has the weaker parent base. Conjugate acid 2 has the weaker parent base. So who is the stronger base? Was our original question. Who's more basic? 1 is going to be the stronger base, because there's nothing to destabilize the conjugate. This looks much better, and so therefore this structure 1 doesn't mind getting protonated as much because it's going to a more stable conjugate. Let's try another example of looking at who is the strongest base. Amines are good bases. Each of these nitrogens has a lone pair, and so we're asking which of them is most willing to be protonated, most likely to be protonated. That would make it a stronger base. And it's possible we could look at the conjugate acids, but in this case, the answer is not going to be found in looking at those conjugate acids, because there's a difference right away in looking at the stability of these 3 parent bases. Okay, and let's take a look at resonance, for example. This first amine has no stabilization, no resonance stabilization. Nothing special about this structure. But when we have a nitrogen attached to a benzene ring, this lone pair is now allylic, or we call it benzylic when it's next to a benzene ring. And so it can have resonance. That makes an N plus and a C minus. And are there any other resonance forms? There sure are. This lone pair is still allylic, and we can go on and move that negative charge around the benzene ring carbons. So there's a difference right away between these two amines. And let's take a look at this third structure. This amine now has a substituent, a group, attached to this carbon. Let's see what effect, if any, that has on the resonance. Well, again, because it's benzylic, we know we can draw a resonance form here. NH2 plus and a C minus. And this can continue down. Oops. We have our carbonyl down here. This is an aldehyde. And this can continue down to put a negative charge at this bottom carbon. Okay, and now when we put this lone pair at this carbon right next to the carbonyl, look what can happen. It's now allylic to that carbonyl pi bond. So we can have a new resonance form that moves the negative charge into the carbonyl. Now, being able to draw a new resonance form is, usually a significant thing, but let's take a look at this. Does this look like it's significant resonance? It actually is, because now we've managed to put the negative charge on an oxygen. The more electronegative oxygen, that's even a better place to be than putting it on the carbon. Okay, so there's an additional resonance form. We can actually move the negative charge up here as well. But I think, again, this is enough to demonstrate a difference by having this carbonyl group attached. And what we can conclude now is that this third structure is the most stable because of resonance. And if it's more stable, the most stable, that means it's the least reactive. And that makes it the weakest base. So right off the bat, if we can find a difference, a significant difference in the stability of our starting compounds, then that can lead right away to a difference in their basicity. Okay, one way we could describe this is we could say that, if we were to protonate this, if we were to protonate this nitrogen, what does that do to all this resonance? It takes away that resonance, doesn't it? Because that would take away this lone pair. So protonation of this compound would be a bad thing, would be unfavorable, because we would lose all this resonance stabilization. So what we could say is that just kind of a comment we can make about this is that the lone pair is unavailable. This is not a very good base because the lone pair isn't around to be protonated to react with an acid. We could say that it is tied up in resonance. What's another good way to describe it? We could say that it's delocalized. Remember, the actual structure is a hybrid of all these different resonance forms. So in all these other resonance forms, there isn't even a lone pair on that nitrogen. The lone pair is spread out over all these carbon atoms and this oxygen atom as well. So the lone pair is unavailable, and protonation, if we were to protonate it and add an H+, protonation would lose that resonance. Would cause all that resonance stabilization to disappear. That's unfavorable. So this kind of resonance makes this particular amine very stable and very unreactive as a base. Okay, and now when we're comparing these two, we would see that, again, this does have some resonance, so this lone pair is also tied up. Compared to this amine, this has no resonance stabilization and has no delocalization of that lone pair. So we could, because these have no stabilization, this is the most reactive, strongest base. And what we could say here, the way we could describe this and compare this to the other ones, is we could say that the lone pair is very available. This lone pair has nothing better to do than to sit around and wait for an acid to react with, so that makes him a much stronger base. This is described as an alkyl amine when we have a nitrogen on an ordinary alkyl group, just a carbon chain like this, and these guys are called aryl amines when you have a nitrogen on a benzene ring. And we'll find that this trend holds true, that aryl amines are going to be much weaker bases than alkyl amines because of this resonance effect. Finally, let's take a look at some common acids and bases. Now that we've seen the sorts of things that can cause a compound to be a stronger acid or a stronger base, let's summarize some of the things that we should know moving forward. Strong acids are defined as those with negative pKa's. These are things that when in water will completely dissociate, will completely protonate water. And these are ones that you should already be familiar with, things like sulfuric acid, nitric acid, the halo acids, HCl, HBr, HI. We'll see those a lot in throughout organic chemistry. H3O+. Okay, anytime you see any of these structures as part of your reaction conditions or as a reagent, you should immediately recognize them as strong acids. And most often, that's going to tell you that the very first thing you're going to do in that reaction is protonate something. These are fabulous proton sources, and they are very reactive, very unstable, and they are going to find a place to protonate. So, so most definitely, if you don't already recognize these as strong acids, you can make up some flashcards so that they'll be more familiar to you. Okay, weak acids are things that generally have a low pKa, somewhere below 16 or so. What falls in this category is this arrangement when we have a carbonyl with an OH. These are known as carboxylic acids. Carboxylic acid has a pK somewhere around 5. It's quite easy to deprotonate a carboxylic acid. Ammonium, NH4+, is also a decent acid, quite easy to donate a proton, as is water, and just an ordinary alcohol. Okay, an alcohol has a pKa closer to this 16. Carboxylic acid has a pKa down here closer to 0. But all of these compounds are quite reasonable to deprotonate. It's quite easy to deprotonate these. Things that we might describe as very weak acids are those with even higher pKa's, above 16. So something like a ketone, these protons next to a carbonyl we'll find are acidic. We can remove them, but it takes quite an effort. It takes a very, very strong base in order to do that. Amines as well. An amine is not easy to deprotonate, but it can happen. Of course, a nitrogen is less likely to lose a proton than an oxygen, so that's why we have a higher pKa here. And if we have a triple bond, a carbon-carbon triple bond with a hydrogen on it, this functional group is known as an alkyne, having a carbon-carbon triple bond. And hydrogens on alkynes are also possible to deprotonate. If you have a very, very strong base, you can deprotonate in these positions. Okay, the other functional group listed we can describe as extremely weak acids. These numbers are so high, above 40, that we could pretty much say that these are not acids. It's going to be so difficult to remove these protons that for all intents and purposes we could say that no reaction is going to happen. There's no base that's strong enough to deprotonate these. Of course, there are exceptions to that, but at an introductory level of organic chemistry, we're never going to see any reactions like this. So here we have an alkene, is what we call it when we have a carbon-carbon double bond. Any hydrogen on an alkene carbon is going to be, it will never deprotonate, will never be able to remove. And the same goes for an ordinary alkane carbon. These carbons, putting negative charges on these carbons would be so totally unstable that that we're never going to see that. Okay, having a triple bond makes it okay. We'll see that down the road when we study alkynes, but alkenes and alkanes will never deprotonate. Okay, so it's good. While typically we're not going to be memorizing our pKa table, it's very good to have a familiarity with these various functional groups and know whether or not it's going to be possible or maybe even easy to deprotonate any of these hydrogens. Okay, and one last example. Let's see if we were to ask about the direction of an equilibrium. Let's say we were given a pKa table and we looked at the following equilibrium, and when we looked in the pKa table, it turns out we were able to find a pKa value for every one of these species. So, well, we know that for the direction of the equilibrium, we know that the equilibrium lies in the direction of the weaker acid-base pair. But how do we use this information to decide who the weakest is? Well, there's something very important to remember for a pKa. Remember what that A stands for? That is the measurement for an acid. pKa's are for acids. pKa tells us something about the strength of an acid. So in the forward reaction, which species is behaving as an acid? The acid is the one who donates a proton, and it looks like the ammonium is acting as an acid, and in this reaction, water is acting as a base. It's accepting a proton. So in this reaction, the pK of water is irrelevant because water is not donating a proton on this reaction. So 9 is the pK for the forward reaction. How about in the reverse reaction? Who is the acid and who is the base? Let's take a look at the direction of that proton transfer. H3O plus is going to H2O, so that means H3O plus is the acid in the reverse reaction. Ammonia is acting as a base in this reaction. So which is the pKa number that's relevant to us? Just the H3O plus pKa, because that's the acid for the reverse reaction. So now we've identified, we've narrowed it down to the two competing acids. We've looked up their pKa's. Of course, we learned in this lesson how to predict the relative acidities. So we should actually be able to, even without a pKa table, we should be able to decide which is the stronger acid, NH4 plus or H3O plus. Do you think you'd be able to do that? That's a very good exercise. I think it has to do with the difference in electronegativities of nitrogen and oxygen. So which of these two species is more stable? I want you to think about that. But we see here that pK of -2 means that this is the stronger acid. pK of 9 means this is the weaker acid. And so where does our direction lie, our equilibrium direction? It lies to the left. You could say that the reverse reaction is favored, or that the reaction lies to the left. So this concludes our lesson on acid-base reactions, and we'll see you back soon at Educator. Thank you.